Hello and welcome back. All of the limit rules that we know and love still apply to limits of sequences. So for example, if we have the limit as n approaches infinity of a sub n equals big A, and the limit as n approaches infinity of b sub n equals big B, then the limit of either the sum, the difference, the product, or the quotient, so either using addition, subtraction, multiplication, or division of these two terms of the sequences, if you take those limits, the limit of the sum, for example, is equal to the sum of the limits of the individual sequences, as long as those individual sequences converge to something, so A and B in this case. Same thing with differences, products, and quotients. With the quotients, you always have to worry about the bottom of the fraction being 0. So if the limit of the b sub n's on the bottom end up being 0, well, the b sub n's converge, it's just they converge to the wrong thing because it's making the bottom 0. Well, then this limit as n approaches infinity of this fraction would not necessarily converge. It would diverge, possibly. So, but this other property here is also something that we know about. You can pull constants out of limits, just like you could in the past. So this k can come out of the limit, and then you have just the limit as n approaches infinity of the b sub n's, which we said a moment ago converged to big B. Right? So for example 5, we can use those limit properties to help us find these limits. For example, the limit as n approaches infinity of -1 over n. We can take that -1 coefficient, bring it out of the limit using that second limit property. And we're just left with the limit as n approaches infinity of 1 over n, which we proved beyond a shadow of a doubt to be 0. That was back in example 2, where we actually proved that limit. It's nice to prove things as much as you can. For the next limit, the limit as n approaches infinity of n minus 1 over n, what we can do is we can break this up into n over n, which is 1, minus 1 over n, which is 1 over n. Then we know that we can break this limit up by sums, differences, products, quotients. We have a difference there, right? So as long as these individual limits of 1 and of 1 over n both converge, then the resulting limit will be the difference of those two. So we're going to have the limit of 1, which is 1, the limit of 1 over n, which again we proved to be 0. So overall we get 1 minus 0, which is 1. In the last example, for example 5, we have the limit as n approaches infinity of 4 minus 7n to the 6th all over n to the 6th plus 3. Now one of the tricks that we learned in Math 180 was to divide the top and the bottom of the fraction by the highest degree term of the bottom, at least the variable part of the highest degree term. So that would be n to the 6th in this case. So if we divide the top and the bottom by n to the 6th, we'll get 4 over n to the 6th minus 7 over 1 plus 3 over n to the 6th. Now we haven't proven that 4 over n to the 6th goes to 0, but you can just think numerically here, and that's most of the time what we're going to be doing. We're not going to be, again, proving every single detail. We're going to just say the limit as n approaches infinity. As n gets really large, 4 over n to the 6th gets really small. It gets closer and closer to 0. You might even write something like this. This goes to 0, and this goes to 0, the 3 over n to the 6th. So you can say we have 0 minus 7 on the top over 1 plus 0 on the bottom, so we get -7. Again, the limit works its way into the quotient, like the top and the bottom of the quotient, into the minuses and the pluses, and so it's going to work its way all into each of those, as long as each of the individual limits exist. So we actually had to wait until this second step, where we divided by the n to the 6th, before we could work the limit in there, because only then did the limit exist for each of these terms on the top and the bottom. Example 6 poses an interesting situation. Suppose we have a sub n, which is the sequence 1, 2, 3, and so on, b sub n, which is the sequence -1, -2, and -3, and so on. And it's asking, does the limit a sub n plus b sub n converge or diverge? Now the way you get this new sequence a sub n plus b sub n is you just add the corresponding terms of a sub n and b sub n. So you take the first terms, you add them together. Let me write out these terms as we say them. So the terms of a sub n plus b sub n would be, well, the first term would be 1 plus -1, which is 0. The second term would be 2 plus -2, which is 0. The third term would be 3 plus -3, which would be 0. And if the pattern continues, we would continue to get 0 on out to infinity. So when we look at this new sequence, does it converge or diverge? If you said converges, that would be correct, because it converges to 0. In fact, it's at 0 the whole time. It doesn't get away from 0 at all. It converges to 0. So it's interesting that even though you might have two sequences that both diverge, that when you add them together, you might get a convergent sequence. So that's just an interesting thing to note. There might be like a cancellation effect going on between these sequences when you combine them together. The same thing could happen if you multiply two sequences together. Like if you multiply 1, 2, 3 with 1, 1/2, 1/3, and 1/4, and so on. You're always going to multiply them to get 1, and so you'll get a convergent sequence, even if one of them diverged. So you can think about these interesting cases with sequences. Now you might also remember from Math 180 that there was this thing called the Squeeze Theorem. And the Squeeze Theorem helped you evaluate, or at least prove, that some limits existed and were equal to something. So here we have the same Squeeze Theorem for sequences. And once again, we're going to have this big N. So if you can show that the b sub n's as a sequence are trapped between two other sequences, a sub n and c sub n, eventually, so big N, little n greater than big N means like eventually, so beyond big N. And if the sequences a sub n and c sub n are both approaching the limit L, then the b sub n's, which are trapped in between again, are going to be squeezed to approach L as well. So if a sub n and c sub n are going to L, then b sub n is going to L too. In example 7, let's use the squeeze theorem to figure out if cosine n over n converges or diverges. What we can do is we can start by writing cosine n is going to be between -1 and 1. We know that for sure. And if you divide all of those terms by n, you get that cosine n over n is between -n and 1 over n. So what we did from this step to this step is we divided by n. What that does is it puts our sequence and traps it between these two other sequences. So let's take a look at these other two sequences and see where they're going. Well, the limit as n approaches infinity of -1 over n, we already said was 0. The limit as n approaches infinity of 1 over n was also 0. So I can write it like this. Both of these are equal to 0. So by the squeeze theorem, the limit as n approaches infinity of the function trapped in between those two is also 0. In other words, cosine n over n as a sequence, and we could put little curly braces around it if we want, or that's optional really, converges to 0. Converges to 0. It asks us, do the following sequences converge or diverge? Converge, in this case. If they converge, what do they converge to? Converges to 0. Let's look at the next example. -1 to the n times 1 over n. Well, if you look at -1 to the n, that's going to alternate between -1 and +1, right? So you're going to have -1 to the n is between -1 and +1, just like cosine n was. So if you divide this by n, you get, or I should say multiply by 1 over n. Let's write multiply by 1 over n. It's the same thing as dividing by n. Oops. Color malfunction. It's just written over here in our sequence as times 1 over n, so I'll just make it like that, times 1 over n. So you get that our sequence is trapped between, again, negative 1 over n and 1 over n. So we can write something similar. The limit as n approaches infinity of negative 1 over n, and the limit as n approaches infinity of positive 1 over n are both 0. So by the Squeeze theorem, the sequence in between, the negative 1 to the n, the negative 1 to the n times 1 over n converges to 0 as well. Okay, so just to give you a flavor of what a squeeze theorem might look like for sequences. Thanks for watching the video, and see you in the next one.